So welcome everyone to the Applied Algebraic Topology online seminar. The speaker today is Bala Krishnamoorthy, and he will tell us about Steinhaus filtration and stable paths in the mapper.
Thank you, Sarah, and thank you, Elkanah, Henry, and Sarah for this opportunity. This is joint work with Dustin Arend at PNNL and two of my students, Matthew Broussard and Nathaniel, who is now actually an ex-student. He is still finding time to maintain Cech TDA. The preprint is available on archive, and I would start by acknowledging funding from NSF and DOE, where Nathaniel was actually interning with Dustin at PNNL through some funding from them. And one word about NSF, I'm actually part of a multi-institution team working on TDA in studying energy landscapes. So this is both an acknowledgement as well as a word or a pitch for this project. This is an NSF HDR project called Delta Topology. We are using persistent homology, Morse theory, and other techniques to come up with characterizations of energy landscape. So I encourage you guys to check it out. So let me get started. The TDA construction of our interest is the mapper, which was originally proposed by Singh, Memoli, and Carlson in 2007. This is a picture that gives most of the idea of what it is about. You have a point cloud, and the goal is to come up with highly compact representations of a space or a point cloud, which quote unquote reveal structure. And that is the big deal here. The pipeline goes like this. You choose one or more of the dimensions or the functions on the points as lenses. For instance, here I have a point set from 2D, which looks roughly like being sampled from a circle with some noise. And let's say we take the height of the points as a lens or a filter, and I cover the range of that function by overlapping intervals typically. So here I have three intervals in 1D or higher dimensions. And then I pull back that cover, meaning I identify the points in the input which have height values in the red interval here. Those are these points. For the green interval, we get what visually looks like two separate sets of points, and the same thing for blue. And then we do a refinement of the pullback, which in practice means you use a clustering algorithm to cluster the points in each of these pullback covers, or you can think of identifying connected components within each of these pullback covers. And then you take the nerve. This is a dual construction. So each cluster is represented by a node. And when you have, so here, for instance, imagine that you're doing a clustering algorithm which clusters all the points in each of these refined cover elements. So I have a node for each of these blobs. And since the left green cover element and the blue cover element have a point in common, I have an edge. And if you have three cover elements in the refinement having common points or common intersection, then you add a triangle and so on. So going from a collection of points to this highly compact simplicial complex in general, and that is called the mapper, or alternatively, the entire pipeline is also called the mapper or the mapper algorithm, mapper construction, and so on. Note, of course, notice that, hold on, I wasn't sure it was my email. Let me mute it, sorry. Notice that we have gone from a collection of points, which could be very large, to a highly compact representation, which still captures the circle. Of course, the big deal about the mapper has been that it has been applied in numerous areas. The applications are too many to cite all of them here, but I myself have used it in applications in biomedicine, criminology data, and machine learning, and so on. The common theme of most of these applications is that people have been using the one skeleton or the graph of the mapper complex for interpretation, for identifying interesting features in the data, even though in general the mapper construction gives a simplicial complex that is higher dimensional. And going further, features in the 1D skeleton like paths and flares or loops, they have been used to identify non-trivial or interesting structures in the data. So the application, in fact, it's been so much so that you could arguably call mapper as becoming one of the main phases of TDA. Persistent homology, of course, is the big deal otherwise. But in terms of applications, in terms of non-specialists using TDA tools, mapper has seen a lot of adoption, let's say. But of course, there's been developments on the theory side also. In particular, there is this desire to give a notion of stability when you do this construction. How stable is that construction? And whenever we talk about stability in TDA, typically you involve the framework of persistence. I want to list a few main results. This is not an exhaustive list. The first such result was given by Tamal and Facundo and Yusu Wong, where they talked about multi-scale mapper. The idea was to use what is called as a tower of covers. So intuitively, if you imagine that interval cover that I mentioned, now if you keep the center of the covers fixed, let's say, and you grow the intervals in some fashion, then the bigger set of intervals will include the older cover as a subcover. Now, if you do that in a sequence, you get a collection of covers, each one including the previous one. The implication is that you get a filtration. The mappers, which are the nerves of each of these covers, will form a filtration, and then so you can involve the entire persistent homology machinery, and then you can give the standard sort of stability result, which says if the input, if there is some epsilon change in the input, then you can bound the distance between typically the persistence diagrams corresponding to the two mappers by some function of epsilon. The other bigger couple of papers that I want to mention here is by Carrier and Odo, who gave a fairly comprehensive study of the stability of the 1D mapper. Their notion also was to consider what is called as a multi-nerve mapper, again, some sequence of covers, intuitively speaking. Then they are able to go to an extended persistence diagram where these features, in particular the paths and flares and so on, which we'll see a little bit more of coming forward, they appear as points in the extended persistence diagram. And again, the notion of stability is the standard one in the sense you can bound, for instance, some sort of distance, bottleneck distance between the persistence diagrams as a function of changes in the input functions, for instance. They also had, along with Michel, they gave a different analysis of parameter selection. Of course, the motivation here is that in most applications, people are still using just a single mapper. These notions of multiple tower of covers or multi-nerve and so on, while they are necessary, maybe not necessary, but they give us a way to characterize stability. At least no open source implementations of those algorithms are known. And people tend to, even now, they try various parameters, look at which mapper looks quote unquote interesting or seems to reveal structure, and then they make their interpretations based on that. I should also mention another kind of different approach towards stability by Belchi et al. They were looking at stability or instability, as they called it, to the clustering step rather than the movement of otherwise. So there are several results in this line, but our motivation came from applications where perhaps a distance or a filter function is not immediately obvious, but a cover is available readily. For instance, if you think of movie recommendations in Netflix, you can cover the collection of movies by the collection of viewers who have rated the movies, or vice versa. You can cover the collection of viewers by the movies, the sets of movies that each one of them watched or reviewed, for instance. But other than that, there is no other obvious metric to readily choose as a filter function or a lens. So can we, these covers can be thought of as abstract covers rather than the intervals that you have as, in the default picture. So can we define a mapper on abstract covers, and which will help us find structure in the usual way? That was our one of the main motivations. But then, of course, stability is always a desirable property. And given that people are still using single mappers for interpretation given data, can we give a notion of stability or define and prove a notion of result on stability from a single abstract cover? And the idea here is illustrated in this example. Let's say we have a bunch of points, and each of these blobs here is an abstract cover. So I'm not using the vertical or y height or the x-axis, x distance as a filter here, but this is just an abstract cover here. And notice in particular the cyan blob and the green blob here, which correspond to these 2 points in the nerve or in the mapper. They have an overlap of just a single point. So I do have an edge. Whenever 2 abstract cover elements have overlap, it creates or it generates an edge in the nerve or in the mapper. So I do have an edge here, but if I remove that just a single point, now suddenly the nerve goes from a loop to just a path. And if we want to talk about paths in the mapper, and let's say we want to, for whatever reason, look at a path from the cyan node to the green node, in the first case, we might want to interpret just this edge, but we might also realize soon that, well, that edge is defined by just a single point in the overlap. The strength of the overlap is low, while the other edges probably all have 4 or 5 points defining the overlap. So perhaps a more reliable path from the cyan node to the green node is the one going all the way around and not the single hop. So that is the notion of stability that, at least in the case of the motivating applications we are interested in, more than what happens if a point here moves a little bit here, or epsilon up or down, or in some sense, right? So can we capture a notion of stability in terms of membership or inclusion or addition of new points and so on? So here's a brief summary of results before I go further. We define a cover filtration from a single abstract cover. Whenever we talk about covers as sets, and a notion of distance, a standard notion is that of Jaccard distance, we generalize that to Steinhaus distance, which is actually a generalization of the Jaccard distance we start with, hence in the title. And it turns out that we are able to prove a stability result, which intuitively says that the cover filtrations, if you have 2 cover filtrations, they are interleaved by the bottleneck distance of the covers themselves. But we are also then able to study stable paths. So once we have the stability result, now let's say we want to look for those kinds of features in the 1D mapper, paths and flares and loops and so on. We define and study a notion of stable paths in just a single mapper, though, rather than looking at sequence of mappers. And the kind of stability or the notion of stability we want to capture is this strength of overlap. That's more important for us here. And we look at a couple of applications. The applications here are not the main kind of result or main goal of this work, but at the same time, they are quite interesting and we think quite valuable. So I will highlight 2 applications, one on movie recommendations and other one on explainable machine learning. Okay, so let me get into the details. Remember the pipeline: lens to cover, pull back of the cover, refine it, clustering or connected components, and then take the nerve. But now I want you guys to kind of leave that notion of, when I say lens, height function or some hypercube in some high dimensions. Instead, you think of lens as just an abstract notion. I cover the lens by this abstract cover. So this is, again, If you want an intuition, think of movies and viewers who have rated the movies. But the pipeline still carries through. I can take the abstract cover and pull it back. For instance, this green cover here, cover element rather, pulls back to 3 different components in the pullback. Then I do the refinement and then take the nerve. So that part of the pipeline is the same. So the big difference is that I'm not insisting that the cover elements have to be only the kind of the default notion that people have, intervals or hypercubes and so on. Okay. Of course, since we are talking about covers, cover elements, we want some notion of distance between cover elements to capture how different they are. So the standard distance of that comes to mind is the Jaccard distance, which is, intersection over union. It measures that. So 1 minus the size of the intersection over the size of the union for a pair of sets. You can naturally generalize that to more than 2 sets or more than 2 cover elements, but it's still 1 minus size of intersection over size of union. And here I have 3, but in general you can have k sets or cover elements, 1 minus size of the intersection over size of the union. But here, when I say size, it just counts cardinality. That's the default Jaccard distance and the generalized Jaccard distance. But Steinhaus generalized that notion by considering general measures. So the only difference we have from the Jaccard distance definition is that instead of just the cardinality, we can consider a measure on those sets. So again, 1 minus measure of intersection over measure of union is a Steinhaus distance. And then we can generalize that to multiple and not pair of cover elements. So 1 minus measure of intersection over measure of union. And that's what we will use in general. But in many instances, the cardinality, just the count measure is sufficient. So when I say cover filtration or Steinhaus distance, Steinhaus filtration, and so on, I will use those 2 words, cover distance, cover filtration, interchangeably. Sometimes I might even say Jaccard, because that's sufficient and you don't have to consider any measure. But the results hold in the case of a measure setting also. Okay. So we first talk about the Steinhaus nerve. So you have a cover script U, and you can give each simplex in the nerve of the cover this Steinhaus distance as a weight. So that's a weighted Steinhaus nerve. That's what we call the Steinhaus nerve. But now, if you think of the weight as a birth time, that immediately gives us a filtered simplicial complex. We can prove that the Steinhaus nerve is actually a filtered simplicial complex. So you start with a single cover though, but then if you use these Steinhaus distances as weights and alternately as birth times of those simplices, then you get a filtered simplicial complex. So going back to the example that I illustrated, for instance, if I look at the cyan and the blue cover elements, I have put in the sizes here, the number of points, 22 here, 18 here, and 4 in the intersection. So the size of the intersection 4 over union, which will be 22 plus 18, 40 minus 4, double counting the intersection. So 1 minus 1 over 9, 0.89 and so on. So you can do that for all simplices. And then if you use those Steinhaus distances as a parameter and filter over that, we get a filtration. So naturally the edges with small Steinhaus distance appear first and they stay on, and then the rest appear. So we get a filtration. So now, rather than using multiple covers which have nice structure, our idea was to somehow use this to capture some sense or notion of persistence. And so as to be able to say something about stability. So here is the stability result. We are looking at 2 covers of a set X. the result we have proved assumes their cardinality, number of cover elements is the same. In practice, they don't have to be, but in our proofs, we do assume. And we use the bottleneck distance between the two covers. So that is a matching distance, essentially a symmetric difference of any two elements that from the one cover and the other that are matched in a matching. I want to minimize overall that the maximum symmetric difference size overall matches. That's a bottleneck distance. So if you are given some bound on the bottleneck distance and the cardinality of the smallest cover element in either cover U and V, that's M, then we are able to say something about the filtrations, Steinhaus filtrations generated by U and V. The theorem says that the Steinhaus nulls of U and V are alpha over M interleaved filtrations. The proof is not hard, but it's kind of technical, but it uses mostly first principles. In particular, we are able to say that without using, at least for me, any of the heavy machinery of categorical theoretical notions. So the intuitive idea here is that if alpha, the distance, the bottleneck distance between the covers is small, then the filtrations are also alpha close in some sense. But also the M, if you go back to the example that I had, the cover elements that are really small might create instability, or when you match it, you might have high differences in the symmetric difference computation. But if all the elements have large size, let's say if all cover elements have at least 4 points and so on, then you would expect that the cover filtration, the Steinhaus filtrations would also be close. So actually a more precise statement is here. So the Steinhaus distance of any cover element UI, i.e. for an index, that is matched with VI in the other cover lies between Steinhaus distance of that corresponding VI plus or minus alpha over M. So that gives some notion of stability for this Steinhaus filtrations. So again, we are not yet using persistence diagram set, but perhaps there is a way to extend this notion to persistence diagram and then connect it to distances between persistence diagrams, but that's part of future work. But the main take-home message here is that starting with a single cover, we are able to give a notion of stability. Yes, Bay?
Dropped quickly, sorry for a question. I'm a little bit confused by the notation. Why is a DST taking one input if that's a distance?
Yeah, it's a cover, right? So a single cover. You can define it. Let me go back.
Sorry, I just was trying to recall the definition of the DST again.
Yeah.
Oh, I see. Okay, it takes sets, and so this is a generalized distance. So you take the sets and look at how much they kind of overlap. Okay, thanks.
Sure. Any other questions?
I have a quick question, if that's okay.
Yeah.
So this is for the Steinhaus distance, not for the generalized Steinhaus distance where you include a more general measure.
It is the stability. I mean, all the results that I mentioned, at least on the theoretical side, they hold for the generalized Steinhaus distance.
I see. So here doesn't seem to be any mention of the measure in this slide.
Yeah, here, yeah, but DST, right? DST includes the measure, right? The DST UI is defined.
Right. So you're saying in the bottleneck distance parameter that sort of measures using the
that
symmetric
is on
differences.
the size. So we are connecting the size of the sets to the measure also.
Okay, so that's constant regardless of which measure you're using.
Sure.
The dB.
Yeah.
Okay, that's great. Thank you.
Yeah.
Exactly. Okay, thank you.
Okay. So after we defined this, natural question was, how is this related to two of the standard filtrations that we study in the metric setting, Cech and Vietoris-Rips complexes or filtrations. So this is where the measure notion, the Steinhaus distance, actually gets used, while in other more direct applications, cardinality of the set is sufficient. So we have a conjecture and a proof in 1D. Our conjecture is that given a finite set in Rn and some radius parameter, which is larger than the diameter of the set, the Cech filtration on X, again, what is that? You put R balls centered at each point and take the nerve, and then look at the Cech filtration of that. That's isomorphic to the Steinhaus nerve using those balls. So here, of course, when I take the cover elements and then the measure, here I'm using the d-dimensional volume, sorry, the n-dimensional volume, sorry, of these balls, and not just the cardinality. Okay. We have the proof in just for 1D, that means intervals in R1. So we are able to explicitly give the mapping to go back and forth for the birth times, the Cech in the Cech filtration and the Steinhaus filtration. It'll be nice to prove the general result. But when we consider the Vietoris-Rips filtration, we have a complete characterization going one way. So the Vietoris-Rips filtration of these points completely determines the Steinhaus filtration for any n. And it's only one way, but we don't have the other way. But we do have experimental evidence for the other way. For instance, when we look at n equal to 2D points, when we do the computation, the persistence diagrams from Vietoris-Rips and the Steinhaus filtration appear to be close enough, but we don't have a full proof. So that kind of helps to situate our Steinhaus filtration with some of the other standard notions. Okay.
So a question
Yeah.
there.
Yeah, sure.
The Vietoris-Rips filtration doesn't determine the Cech filtration, right?
Yeah, these are two different. I mean, I'm looking at
Yeah.
equivalence to Cech and Vietoris separately.
So I'm wondering whether you would expect, suppose you were able to prove that the Vietoris-Rips filtration and the Steinhaus nerve completely determine each other. Would you consider that to be in support of your conjecture or contradicting your conjecture?
Good question. I don't know. I think it will support, but I'm not sure. I mean, as you said, they don't. The Vietoris-Rips does not completely determine the Cech. There are more things that show up when you look at three-way, four-way intersections. So, yeah, it's a good question. I don't know off the top of my head. Sorry. Any other questions?
That's it for me.
Okay. Thanks, Michael. All right. Let me talk about paths now. This was one of the motivations to start with. We want to highlight paths where each overlap is strong, as in defined by multiple points in the intersection rather than small number. So it turns out our notion of stability helps us to define stability, a notion of stability of paths naturally. So here I'm talking about a path in the one skeleton of the mapper. So path P, we can say, is row stable if the Steinhaus distance of every edge in the path, in a bottleneck sense, is at most row. So intuitively, what this captures is that every edge has at least some level of overlap. If you look at numbers, then every edge has 5 points defining it, for instance. Okay. And then we can seek or try to find a more stable ST path. If you have two nodes in the mapper, one skeleton, and you're looking at paths going from S to T, we say that the most stable ST path is the row stable ST path for the smallest row. Remember, rho is now the distance and not the strength of overlap. It's the complement of that. And if there are multiple paths between S and T with the same row stability, then we can take the shortest in terms of number of hops or number of edges. So we would first want to get all edges quote unquote highly stable, but then if there are alternative options at that level of stability, then we can go for small number of hops. So the big advantage of our notion of stability previously is that that result automatically implies that paths are stable at the given level, because the stability itself captures this notion of how strong the overlap is in each edge, for each edge. So if you have a cover where all the edges are highly stable, as in all the overlaps are strong, then if you look at paths in the one skeleton, well, of course, all the paths will also be highly stable from that point of view. So this is kind of different from the philosophy of stability as defined in the other notions. So there, even though we can bound the distances between persistence diagrams, you can't necessarily say directly anything about, or at least anything concrete about, which paths define the points in the persistence diagram. Of course, so if you take a loop, that will correspond to a point in the one-dimensional extended persistence diagram. You have a notion of stability, but then you can't necessarily certify that it is the same loop. So even if the point in the persistence diagram did not move much, you are not able to certify that it is the same loop which generates that point. So it's more going towards the generators. In our notion, those two are given by the same idea of stability. So if you have a loop where each edge is row stable, then when things move, I would still say that it's the same loop which will be there. So that's a slight advantage over the other notion. Okay. So of course, a short path in the 1D mapper need not be the highly stable path or the most stable path anyways, and vice versa. So you might want to take a large number of hops or a path with a large number of edges, and that might be more stable than a short loop. So these two notions of short paths versus stable paths, there is actually a Pareto frontier that we might want to explore. And so rather than giving the most stable path or the shortest path from S to T, you might want to study a sequence or a collection of them at the Pareto frontier. And that's what we do from the applications point of view. So now those are kind of the summary of the more theoretical results. I want to highlight a couple of applications. The first one is more directly coming from the initial motivating application of movie recommendations or recommendation systems in general, where you have abstract covers readily available, but a suitable filter function or a metric may not be immediately available. Of course, people can always endow a desirable metric on it, and that's how people handle things. But our goal was to, of course, use abstract covers directly. So as a direct application, we looked at a MovieLens 20 million data set. This is an open source database of more than 20 million ratings by about 140,000 users, more than 22,000 movies. So we did this pipeline. Okay, so we built, we looked at movies covered by a collection of users. That's the cover, and so we just used the cardinality here, so the Jaccard distance standard, well, generalized in terms of multiple sets. Then we built the mapper, and then we wanted to look at the stable paths. So naturally, anyone who watches Netflix is familiar with this idea of movie recommendations, where as soon as you finish watching a movie, Netflix will suggest some other titles. So if you watch this movie, you would also like to watch this other movie. But now let's say you just watched the movie Mulan, which is at least the original version is an animated adventure movie. But then your friend watched Moulin Rouge. The similarities in terms of pronunciations of the titles apart, they are very different movies. That's a musical romantic movie. So you won't expect Netflix recommendation systems to suggest Moulin Rouge to you when you just watch Mulan. But let's say your friend wants to somehow convince you to watch Moulin Rouge. So rather than going just one hop from Mulan to Moulin Rouge, maybe there is a sequence of movies that you could watch, starting with Mulan, and so that you are eased into watching Moulin Rouge. It turns out, yeah.
Can I interrupt with a question, if that's okay? So
yeah, sure.
there are 140,000 open sets here, if I understand correctly? One for each user?
Yes.
Okay. That's a lot of open sets.
No, sorry,
okay.
It's the other way. Sorry, I mentioned it the other way. So we cover the users with movies.
So there's 22,000 open sets.
Yes. Yeah.
Okay. And you're trying to find a path therefore between two people or between two movies now?
Two movies. So, or actually nodes. Of course, these are nodes in the mapper. So each node is a collection of movies. So we look at a path from the node that has Mulan to the node that has Moulin Rouge. Of course, there might be other modes.
Right.
There might be other movies in the cluster in each case.
That makes sense. Okay, thank you.
Okay. So we looked at these paths, stable and shortest paths, and these are the recommendations. So if you have only a little bit of time and you still want to transition from Mulan to Moulin Rouge, you would watch The Little Mermaid and Shrek and then Moulin Rouge. So it's still not just direct one hop, but still some of the transitions might be still appear jarring to people who are familiar with all these movies. So, but if you have a lot of time, then you would follow the most stable path. Of course, it's 10 movies going from Mulan to Moulin Rouge, so 9 transitions. But the transitions in each case are more gentle. And so you will be eased from one genre to the other. Of course, what the method is capturing here is that there are several people who have rated both Little Mermaid and Snow White and Seven Dwarfs highly. And there are several other people who have rated Snow White and Seven Dwarfs and The Lion King favorably, and so on. So that would make sense to go along. Okay. Yes, perhaps a PG-13 rating. That's another thing that we can put on the weights. That's a good point, Bay. So this is a nice application of the stable paths versus shortest paths directly. Okay. As a second application,
Can I ask another quick question? So just 2 follow-ups to make sense of this. So how much longer is it to go through Pulp Fiction? So it's just about, when you say the shortest is the number of steps total.
Yes.
Okay, so this is the most stable. Is there a way of quantifying, so in terms of how much more stable is it?
Mm-hmm. Yes, we do have the row value, right? I mean, naturally, shortest would not be as highly stable as the most stable path. So that is that's captured by the value of the Steinhaus distance.
And just as an intuition for trying to make sense of this geometry, would you expect, say, 2 movies to have relatively few geodesics between them, or are there many paths?
That depends on the 2 movies. In fact, we were in our paper, we have a couple other examples of these quote unquote unnatural or unexpected transitions. So naturally, if you look for movies that are otherwise highly similar, then you would expect them to have maybe multiple geodesics, but also they would also come close by. Maybe they are even in the same node, right? But if they are not in the same node, there would be, small hops, as in short paths. But what we found interesting was, okay, let's take movies that are otherwise considered quite different from different genres. Then we look at these paths. In the examples that we considered, there were, in one case, we had a hop of just 3 movies as the shortest, but 5 or 6 movies as the most stable. So it really depends on the movies you would take.
Okay, very interesting. Thank you.
Yeah, that's great.
So just a quick question. Maybe I missed this. How did you choose cover for this case?
So the 22,000 movies, each movie. So the movies rated by the users, right? So it's like a bipartite graph otherwise, typically. So you can cover movies by the users that you rated each movie, or the other way.
Yeah.
So our cover elements are this 22,000 movies.
Right. But I'm just saying, like, the point, your high dimensional point, each point is a movie, but what is because you're talking about abstract cover. So what is your design of those cover elements? Are you growing a ball surrounding each node, or like, how did you arrive at cover?
It's just the collection of users that rated each movie, right? That's the set. And then
I'm talking about like, if I'm thinking about, I have a point cloud on 2-dimensional space.
But he doesn't have a point cloud, but he's not using the ratings to embed the movies in high dimensional space. They're just sets. And then if, it's a bipartite graph, as you said, and then there's edges when there's a rating, and then each, so there's no high dimensional space.
Yeah, we are not looking at an embedding.
Okay.
Yeah, this is completely abstract.
Okay.
Yeah. Okay. So let me give the second application. Yeah, go ahead.
Could I ask a silly question also? So what I understand is you are covering the movies with the ratings. So all you care is that somebody rated it.
Yes. So good question. How good is the rating? We did not involve that, but we can involve that. So that's where a Steinhaus, the mu, can be actually used as a rate. Right now we have not done it, but that's a natural extension.
Okay, thank you.
Yeah. Okay. So let me talk about the second application, explanations in machine learning models. This is, again, perhaps it'll come out as just a toy application, and that's what it is. Our goal is, of course, is not to invent or come up with a method to improve the accuracy of the prediction of the model and so on. We are just saying, if you give me a trained model, I'm just trying to understand what it's learned. So as an experiment, we looked at the Fashion-MNIST dataset. It's a standard dataset where there are more than 70,000 images. Each image is a 28 by 28 pixel image, and each image belongs to one of the 10 classes, like sneakers, ankle boots, purse, and so on. So 10 fashion classes. Here's what we did. We built a logistic regression predictor. So that's, again, a very unsophisticated prediction model. But our goal here was not to come up with the most accurate prediction model. We are just trying to explain what any machine learning model could learn. So this seemed to be appropriate. So we built this prediction model using a 5-fold cross-validation, and we were able to get a 93% accuracy of prediction on the test set. And we are going to build, we're trying to see how this model has learned these 10 classes. So we could use a 10-dimensional filter. So here, there might be covers or distances directly or immediately available. This is not the same setting as the movie recommendations, where things are really abstract. But we still wanted to be able to visualize things. So we did a dimensionality reduction from the 10-dimensional probability to a 2D filter using UMAP, using just standard parameters. Then we built a cover filtration on the mapper using this 2D filter as the 2D reduced probability measure, UMAP reduced probability measure as the filter. That's what we used, and then we built a cover filtration on the map. So in some sense, all we are doing here is once we get that 2D mapper, we are endowing the overlaps, in particular edges here, with that Steinhaus distance. In this case, it's just the Jaccard distance. Okay. And we wanted to then look at the paths, stable paths. And our motivation was that can we somehow gain some understanding of how the model has learned these classes from these paths. So this is just one sample output. We are looking at, let's say, sneaker, sandal, and ankle boots. These are actually stable paths of up to 12 edge length or 12 hops from the nodes corresponding to sneaker, sandal, and ankle boots. I'm listing for each node, I'm listing representative members from the 3 classes. And if there is an image missing in this node, for instance, there was no ankle boot in that node in the mapper that had sneakers and sandals, but no ankle boots. So then we look at it, and this now becomes kind of subjective. We couldn't really quantify, what this is showing, but qualitatively speaking, we are able to see that, for instance, the model is naturally getting confused between the sandal with an ankle loop and an ankle boot, for instance. So in general, the height of the boots seem to be going up from kind of a really flat sneaker to even a sneaker with a higher ankle. That seems to be the trend in both cases. So that's the transition. But then we are able to glean more understanding of why the model might get confused. So again, so this node in the mapper has representatives from all 3 classes, which means that the model is not able to, the trained model is not able to distinguish them as well as if they were in separate nodes. And then we can look at those images or representative images, and we are able to give some sort of explanation for why that is happening, or why the model learned it in this fashion. And these paths are helping along the way. Okay. Of course, I should mention work of Bay here. She gave a talk, I think, a few months back, maybe April or May, where they did something similar, but on more realistic machine learning models on neural networks and their activations. They also used this, at least at the base level, they also used a mapper, and then they were identifying loops and flares or bifurcations and trying to interpret them. One small difference, of course, is that in our case, we are identifying the paths using the notion of stability. And so I encourage you guys to check it out, check base work out. Again, our goal here was not to improve the machine learning performance, but if you give me a machine learning model, we are trying to maybe glean something about what it does or how it has learned. Okay. So that's another application. Okay, so maybe I will then wrap up with some open questions. In our stability result, we assume the cardinality of the 2 covers is the same. That was used in our proof, but then naturally every cover need not have the same cardinality. So how do we handle covers with different cardinalities? There are some notions, for instance, of Gromov-Wasserstein distance, where you can have, probabilities which don't have the same mass to start with. They don't both add up to 1, and you can have notions of distance between them. Perhaps some of those could be useful here. Proof of the Cech equivalence conjecture is interesting. Of course, the equivalence that we showed in 1 dimension, it's kind of from first principles. We wrote down explicit formulae to go back and forth. doing the same thing in higher dimensions seems somewhat tricky, but maybe there are other ways to attack it. And talking about this covers with not same cardinality, there's another notion. In fact, our stability result tries to capture this strength overlap of edges. The standard previous notions of stability for multi-nerve mapper, multi-scale mapper, they bound, for instance, bottleneck distance between persistence diagrams in terms of variations in the distance, variations in values of the functions, for instance. So it would be actually nice to combine the two notions of stability. So if you imagine the blob picture I showed, and suddenly one point just disappeared, that's the kind of stability notion that we are trying to capture. In the other existing notions, you can think of what they are trying to capture is when the point moved and by not too much, right? Can we combine the two notions? That would be nice. So perhaps there's a way to combine them into a single framework where stability to inclusion or addition or removal versus movement are both captured. Okay? And finally, going into applications, we talked about row stable paths, and naturally the flares or loops are also interesting, and then the stability notion of paths directly carries over to row stable loops or row stable flares. Essentially what we are saying is you can define a loop where every edge is row stable, right? So what would those features imply or mean, for instance, in the recommendation systems context or in other applications? That would also be of interest. So I think I will end here. Thank you.
Thank you, Bala. So now I would ask everyone to unmute themselves so that we can clap.
Thank you.
Okay, so we had a very lively discussion today already during the talk. That's why I didn't want to interrupt. But if you have questions, if you have more questions, now is the time to unmute yourself and ask them.
I saw Nahid raised his hand, so
yeah, go ahead.
Nahid, why don't you go ahead?
Hello. I had a question about the computational complexity of the stable path algorithm. So let's say if in the cover you have, in the mapper you have n covers, then what is the complexity of finding, let's say, p stable path?
So it essentially amounts to finding enumerating paths in an undirected graph. So we talk about that in our preprint. It's you can, if you want to identify all stable paths at some level row, then you'll have to consider possibly all S and T pairs, but that becomes a generalization. Well, not generalization. That's a little special case of the Floyd-Warshall, all pairs shortest path kind of a deal. So it's polynomial, but because it's undirected, it's a little, even there are other techniques which make it more faster. But if you give me a specific S and T, that it's actually even more fast. I don't know the exact big O bound off the top of my head, but it essentially amounts to shortest path computations in undirected graphs.
Okay, so I have another question is about the stability result that you have. So just as a clarification, you use the counting measure here, right? The result only holds for the counting measure, not in general animation.
The alpha bound is from the counting measure, but the result connects that to general mu's. The bottleneck distance is for the Steinhaus distance. So it does count. That is the main idea, right? We want to associate the counting bound on the counting measure distance to a more general measure. So in the Vietoris-Rips and Cech equivalence framework, we did have to use the mu. Yeah.
I see. Thank you.
Okay, and then we have Bei raising her hand.
Yeah, I keep forgetting how to raise a virtual hand and actual hands. But my question is actually following also this this stability results where do you have any constraint over the type of measure that this result hold? That what is I mean, is it any measure is going to work, or what is sort of, is there like sort of a class of measure that this results hold?
No, we only bare minimum assumptions so far. So any measure should work.
Okay, so my second question is actually on the stability of the path, because as you mentioned that those are different notion of stability, right? The first notion is sort of in terms of interleaving, but it seems to me what you call stable path is a path in the mapper graph where the weights is sort of like every pair of there's a sort of good weight on the edge, right?
Yes.
So if I take any subpath of a stable path, I think by your definition, is it automatically stable, or that's it sort of like okay?
Every edge is at least row stable to start with, so a subpath will have that, but it could also be more stable, right? Because it's a subpath. So the bottleneck edge may not be part of the subpath, so it might be more stable, but certainly subpath is guaranteed to be row stable also.
Right, but is there also a notion, because I feel like so there's a notion, the classic notion of stability is with respect to perturbations, right?
Yes.
But your stable paths, is there a notion? I mean, it feels like there is a connection because, when I'm thinking about perturbing my cover, the moment I perturb the cover, I start influencing the weight on the edges. So there seems to be a connection between how much I perturb the cover and how that influences the weights, which then influence what you call a stable path. Which say that, like, for example, if I'm going back to your bottleneck distances, this is sort of like one way to measure how closely those two things are. It feels like because you can apply that stability to the entire sort of mapper graph, you can also, of course, apply it to the subgraph, which is a path. So in a way that even there's stability in terms of perturbation for the path as well.
Good point. Yeah, that should work. We haven't considered that, so yeah. So what you're saying is, if you just take a path and then look at subpaths of that, and then we talk about a stability similar to our main result just for that subpath.
Yeah, something to that effect. Of course, this is just me thinking about it for 2 minutes, but I'm just thinking like there seems to be a connection between what you call stable path, which is not the classic notion of stability, but in fact, there is an underlying connection between the perturbation of the cover with respect to this weight on the edge. So I feel like there is a connection there. I can't make it precise yet, but I think there's a connection.
Sure. Yeah, certainly worth exploring. Thanks.
Okay, so just because we're a little bit pressed for time, thank you again, Bala. I will stop the recording, but feel free to continue with the discussion once the recording stops.